There's one in your computer, your phone, and your smartwatch. You don't need to know how it works. You only care that it's fast. Golem is fast. And here is you, needing to simulate a neural network. But your little computer just isn't up to the task. But if you connected to Golem, you could simulate neural networks, sequence DNA, render complex imagery, or whatever you need to do, in a fraction of the time. Let me show you how it works. Golem is a distributed supercomputer. It taps into a global network of unused computing power, and it's decentralized. This means that no one owns it, and anyone can use it, even you. When someone has a job for Golem, it automatically finds the best computers available for the job, and pays them for the power they provide. One of them could be your computer. That could be your money. Whether it's training artificial intelligence or rendering physical models. Golem scales with the task. And it's all made possible thanks to the Ethereum blockchain. What's more, developers can tap into this network by building apps on its platform, creating infinite possibilities. So get ready. Golem is the future of computing. It's just a matter of time.
Yeah, so we're live on mainnet with this project, Golem. And the promo video is mostly rendering and compositing, and the first use case for Golem and for this mainnet release, which is called Brass, it is also rendering, so photorealistic rendering, to be precise. And yeah, how it started, because just before our crowdfunding, we had this idea of distributing computations in a decentralized fashion, and to do this, we started with a simple, very simple proof of concept that was just a hard-coded renderer inside Python, well, not even container. It was Python renderer hard-coded into a provider. Each provider had to implement its own scene, and we were computing. Well, the scene was computed, and the results were sent back, so each provider had to have the same scene hard-coded. It was just a proof of concept. It worked. Later on, we added a few additional features. For example, we separated the rendering from the provider itself so that the provider could host multiple renderers. And it worked as well, so it looked pretty easy. So we ended up with something like this. It was an intranet renderer with all the features that current Brass has, but only computational-wise. It appeared that there were quite a lot of challenges ahead if we take into consideration that we want to move to peer-to-peer network and not to run it in a control environment like this. Because right here you can share your computational resources relatively straightforward, and there are quite a few platforms that allow you to do so. We just wanted to make sure that the computational component works as expected, so that the tasks are split the way they should, that they are computed on providers as they should, and they get back to the requester and can be merged into a final image, and that we can replace renderers on providers. And it was fine. But what Brass is a mainnet renderer on mainnet Ethereum, where real GNT are used to pay from requesters to providers for the work, and it posed quite a lot of additional challenges, which we have solved. So first of all, the rendering use case is in general non-deterministic, which is hard. Non-determinism comes in various flavors, mostly from different OSs, different GPUs, different platforms, different floating point encoding standards. And it means that we cannot use existing technologies for consensus to verify that the job submitted to the network was computed the right way by providers in the network. So we need to come up with some other measures of verifying and comparing results. So this is inherent to our setting, and we believe that quite a lot of tasks that we're going to have implemented on next version of Golem are also non-deterministic. Well, most of them would be. And it poses quite a lot of problems that are not very prominent in, for example, blockchain, where you have deterministic computations all down the road. So this verification non-deterministic use case is, well, for rendering, we know what to do. It's still hard, but we know how to approach it and how to tackle it. As you can see, there are two important steps in this verification. Auto-verification is a matter of using some metrics to compare images and some transforms which enhance features of those images that are important in verification. It may slip if a live person tries to verify results, but are prominent and can be easily catched when compared by an algorithm. Still, the last stage is manual verification because it's up to the requester to decide whether the result that he or she was sent back is really the one that should be sent back, even if auto-verification is unhappy with it. But the point is that in such setting, we cannot compare bit by bit, and we won't be able to do it. So this was a challenge. This still is a challenge because in rendering we know what to do, but there are a couple of different ways rendering can be split into, well, rendering tasks can be split into subtasks, and verifying those subtasks may require different approaches in terms of auto-verification. So the general scheme is like this, but auto-verification itself encompasses quite a lot of different algorithms. And the third one, securing the network. Well, when we were in this isolated intranet environment, it was quite easy. Right here, we are in the peer-to-peer setting, and we have to take game theoretical considerations into consideration. And it means that either we can make sure that the network self-balances in terms of game theory, or we have to secure it, well, additionally, just to make it more tamper-proof and more malicious providers-proof. So we introduced another element to this puzzle. This is called consent. And it is there to help us secure the network and make sure that all actors in the network can resort to a trusted party that can resolve their disputes. It is not required in blockchain, where, for example, we have proof of work and majority votes. Right here we have, when we calculate a task, we build as small subnetworks where consensus is very hard because there are not too many participants and it's easy to be malicious node and cheat on this other's party. So consent is a third-party service that is optional, but in principle can help you with either forcing transfers for your work or arbitrage when someone cheated you and didn't pay. So those three challenges were pretty hard to tackle. We managed to do it. We spent a significant amount of time trying to solve this one, for example, by preparing a deterministic renderer. And even though it can be done, it's completely non-feasible, because when we have an open source renderer, we can try to do something with it, but we would like to implement proprietary rendering engines on top of Golem, which means that we won't be able to touch the source code of the renderers. So we had to come up with ways of dealing with this problem without touching a single bit of the binary being executed on Golem. So we moved to mainnet. It happened, well, approximately a month ago. And Golem has been running on the testnet for quite a while, I believe in more than a year. And the project is in development for almost 3 years. So the last month was Golem on mainnet. It proved to be working well. There are approximately order of 1,000 active nodes. It's Ethereum mainnet, so the real GNT is used to pay for the jobs completed in the network. And, well, as you saw in the movie, parts of this movie were rendered using Golem. So, well, in fact, this is Blender, and this is Blender run on top of Golem. And these parts of animations that we prepared for the final cut were rendered on Golem, and it was quite a significant speed up. It was almost 12 times faster than the native Blender. This native Blender was run on this i7 CPU with 8 threads and 32 gigabytes of RAM, and it really, well, made a difference. I'm going to present you the comparison between those two renderers render tasks at the end. So yeah, we're live, it works, and we're very happy with it, and working towards making it even better. So we solved those, we're solving still those 3 challenges I presented, but we believe that we can make it even better, and we should do it even better in terms of trust in the network, because in fact the notion of trust in this network is that there is no trust at all. There are some nodes behind, there are some IDs. Those IDs are nodes who provide some computational power, some resources, but other than that there is no external notion of trust or reputation for them by default. So it would be great if we could, for example, use some technology or some algorithm that would assure us, or at least enhance the chances of getting the right computations in a significant way. So the very promising direction here is SGX. It's Intel technology, software guard extensions. SGX is a technology by Intel. It's enhancement to the Intel CPUs. And this technology bases on the fact that your binary can be run inside a container, and this container is isolated from the host. So when a user runs a payload, binary payload inside enclave, this container, then it is in practice, in theory, completely isolated from the host. So this is a great promise. In addition, this is a full-fledged computer. Maybe not a very efficient, well, it is efficient one. It's limited in terms of memory, but it's very efficient, which is very important because, for example, we can use some zero-knowledge algorithms here and solve the problems, but it would be infeasible and it would be slow. Right here we have the solution which is almost as fast as the regular CPU and secure at the same time. So this is the SGX. Unfortunately, it is limited to computations only, and what we need in Golem is something more, and we need generic computations with generic payloads. And that's why we work on Graphene. Well, we in cooperation with Invisible Things Labs, work on Graphene. Graphene is a library that simulates OS from the perspective of application. And this is great because application can be run inside enclave in a secure manner without ever even being touched by either a developer or anyone who has to tailor it to this enclave scenario. So we can take an arbitrary binary, put it into this graphene. This is locked inside the enclave, and only by very thin layer of API it transmits data to host and true host. So this channel with untrusted part is very narrow, which is good, and it is, well, it is set, so it cannot be changed. In terms of enclaves, if you would like to communicate with host, you have to manually specify it, which increases the attack surface. And right here, it is set once and for all. So it is known, it cannot be changed, which is good. So we have arbitrary binaries with well-known attack surface, which is small, which is also good. We are able to run Blender inside this setting. So from our perspective, it is a very, very big step towards, well, trustless network with trusted parts that we can be sure that return reliable results. And they can be used, for example, to verify results from other nodes, regular nodes in the network. So this is what we're working on right now, and we believe that this is the good direction, at least in terms of distributing computations. Not only for Golem, but for Golem especially. And how can it be used in our network? So there are 2 approaches. First is consent, because right now consent is an additional service that is implemented as a sort of server or server-ish architecture. With SGX or Graphene, it can be more or less distributed without any effort, because SGX nodes, like this, can create trusted channels between enclaves on different hosts, so that no one can see the data transferred between enclave on one host and another host, which means that the consent can communicate with SGX nodes and in a secure way and use it as a computational backend, for example, in a distributed manner. It can be a peer-to-peer distributed computational backend, which is something I believe quite new. And from the other side, requester can send its requests to both SGX nodes to make sure that the computations are valid, or to regular nodes just to have the results either a bit faster or a bit cheaper and just verify the parts that are very important, or all parts, using SGX nodes. So there are two sides that can use SGX nodes in Golem network, and this makes perfect sense because for computations that are not, for example, very RAM intensive, the efficiency is comparable to the native CPU, which makes it a very, very good and seamless experience for requesters. So this is what we come up with. This is the kind of the future for our technological next big leap, I believe. What we are planning to do additionally is something that you may expect, because we have rendering, we have this technological step, but we also work on allowing GPUs, allowing machine learning, which can mix pretty well with this technology as well. Well, not GPUs, machine learning and verification. And additionally, we plan to add, this is important in terms of consents, licensing schemes for proprietary software. Because when you use a proprietary software, then you also have to use this layer to verify, and you have to use consent to implement schemes for paying from providers or requesters to the software developers. So this is this, if someone prepares a proprietary renderer, for example, then part of the payment should go to this software developer. And this can be hosted on consent, and in SGX it makes sure that these transactions take place and that they are valid. So yeah, thank you, and I'm going to show you this comparison between Golem and native Blender. The Golem was run on i5 processor, Blender was on i7 processor.
Using Golem makes rendering simple and quick. To show this, I will compare rendering times between Golem and Blender. After launching, I start in the Network tab. To create a new task, I go to the Task tab to drag and drop my blend file to begin rendering. The file is approved, so I'm applying a default resolution, choosing the frame range, format, and output location. Now I'm scrolling down to the task settings and filling them out according to the file I want to render. You can check how to best prepare your render task in Golem's documentation on our website. The cost of the job should be around 6.67 GNT for this task. I'm now starting Golem and Blender at the same time and waiting for the rendering to finish. You can see the progress bars below the screens. Golem is connecting to nodes on the network to complete the render. Blender is using only the power of my local machine. Golem is moving forward much faster. Golem has finished first. Blender is still at 9%. The total rendering time on Golem was 40 minutes, and we still have to wait for Blender. It's finished, and it took about 8 hours 11 minutes, about 12 times longer than Golem. To see my job, I'm going to the output location I provided earlier. All my frames are there, so I'm checking on them one by one. And here is the final result.
Yeah, so actually I rendered this part, so it's this 12 times speed up was really there. I had it almost side by side and captured both screens. So it works this way. Maybe it's not the largest scene because it's less than 40 megabytes, but still it was capable with all these transfers and collecting results to render everything 12 times faster. So I believe that there is room for at least 2 times speed up if enough fast nodes are present on the network. So thank you very much.